Elijah Martinez, and this is Group 1 at 8:30 on Lab 9. In today's lab, our group is exploring one of the more familiar but surprisingly complex forces in everyday physics, which is friction. Whether we're walking, driving, sliding furniture, or even writing with a pencil, friction is constantly shaping how objects move. But despite how common it is, friction is one of the biggest reasons real-world motion rarely matches the clean, ideal predictions that we see in physics equations. And that's exactly what we will be investigating in this lab. Our objective is to conduct an experiment that lets us measure two key quantities: the coefficient of static friction and the coefficient of kinetic friction between the materials that we were given. Static friction is the force that keeps a motion from moving when you first try to push it. And kinetic friction is the force that acts once the object is already in motion. One important thing that we already know from physics research that is the coefficient of static friction is always greater than the coefficient of kinetic friction. In other words, it takes more force to start the motion than it is to when it's already in motion. This idea goes back to the classic studies in tribology, which is the science of surfaces in contact. Researchers like Bowden and Tabor showed that friction isn't just about roughness. It's about the microscopic contact points that form between surfaces. These tiny junctions must have been broken for motion to begin, which is why static friction is stronger. Once an object is sliding, fewer of these junctions form, so the friction force drops. Our experiment today gives us a chance to see the difference directly in our data. Friction isn't just a classroom concept. It's a major factor in engineering, transportation, and safety. For example, the friction between car tires and road determine how quickly a vehicle can stop. Road engineers actually design pavement textures, and tire companies design tread patterns specifically to optimize friction under different weather conditions. So the coefficients we're measuring today are the same kinds of values used in real-world design decisions that affect everyday life. By the end of this lab, we will have collected data that lets us calculate both friction coefficients for our materials and compare them to what the literature predicts. More importantly, we'll see how firsthand friction shapes motion in the real world and why it's such an essential part in physics and engineering. Now I will be describing the materials that we will be using in this lab and how we use those
For this lab's materials, we will be using a crash cart, track, and wooden block that will be placed on top of the cart. If applicable, students were also allowed to add more weight to the cart via different types of blocks made with different materials, thus increasing the overall static coefficient. For our experiment, we chose to go with the wood block. After weighing the material that we used, we placed the cart at either end of the track and elevated that end, which we will then measure to get the height at which the cart transitions from static friction to kinetic friction. From doing this, we are able to get our angle theta combined with the data we gathered from the carts that is connected to the capstone software to acquire the average acceleration when the cart is in motion. The more constant, the better. We will then proceed to repeat these steps 3 more times to eliminate the error between the theoretical equation and our real-life experiment. I will now be handing it over to David, where he will then explain the procedure for this lab.
Good afternoon, my name is David Maldonado, and I'll be in charge of procedures for lab number 9. Our objective for today is designing and conducting an experiment whose data will allow us to show and determine both friction coefficients successfully with the sensors and measurement device provided in our table. By definition, F equals UN, a static friction force will have a static coefficient of friction in the same way kinetic friction will have a kinetic coefficient of friction. If we have an object on a flat surface being pushed or pulled by force P and it does not move, hence static friction, or moves at a constant velocity, kinetic friction, by Newton's law, the friction will be equal to the force P then. U equals P over mg. If If you have the option of inclined plane with an angle O and does not move or move at a constant velocity by Newton's law, the friction will be equal to the weight times the sin of the angle, and the normal will be equal to the weight times the cosine of the angle. Thus, U equals tan O. In the case when acceleration is different from zero and the surface is flat, the kinetic friction will be U equals P minus mass times acceleration over mass times gravity. In our case, when we have an inclined plane, the object sliding down and the acceleration is different from zero. U equals negative acceleration plus gravity sin over gravity cos. We'll figure out the measurements with the device provided and when we calculate, and the best case you can use. Set our equipment to take measurements. We'll be using table 3 value for the static and kinetic coefficient of friction. We'll be conducting 3 trials and then the average at the very bottom. After this, we'll discuss what is the importance of repeating more than once time your experiment, what is the learning you take from today's experiment, and how to share your ideas to contribute to the design of the experiment.
This is Alejandro for data and data analysis on Lab 9. For Lab 9, we were tasked to get a mu S and a mu K for 3 different trials in order to get our averages. Before starting the lab, we decided to go with the angled form, following steps 2 and step 4. For the first step, we have to find an angle where the car is barely starting to move. Measuring that out, we got the distance, which was 120 centimeters, which we converted to 1.20 meters, and a height of 14.5 centimeters converted to 0.145 meters. Plugging that to the inverse tan function, we get 0.145 over 1.20, which gives us an angle of 6.89. We plug that into our mu S formula, which is tan of our angle, which gave us a mu S of 0.121. For our mu K, we switch our angle to be slightly higher in order to get the car moving at a constant velocity rather than barely moving. This switched our tan angle to the same 1.20 meters of distance, but the height switches to 0.17 meters. Plugging that into that inverse tan formula, we get an angle of 8.06. For our acceleration, after running the trial, we got an acceleration of 0.128 meters per second squared on capstone. Using those numbers, we plug it into our mu K formula, which is negative acceleration plus gravity sine angle divided by gravity times cosine angle. Plugging our numbers in, we get negative 0.128 plus 9.81 sine of 8.06 divided by 9.81 cosine of 8.06, which gives us a mu K of 0.128. Moving on to our second trial, our new inverse of tan formula is 0.148 divided by 1.2, which gave us an angle of 7.03 degrees, which we plugged into our MS formula, giving us tan of 7.03, which gave us mu S equaling 0.123. For MK, our angle was the inverse tan of 0.18 divided by 1.2, which gave us an angle of 8.53 degrees, which we plug into our MK formula, negative 0.097 plus 9.81 sine of 8.53 divided by 9.81 cosine of 8.53, which gave us a mu K of 0.1399. For our third trial, we got new inverse tan angle of 0.15 divided by 1.2, which gives us an angle of 7.13 degrees, which we plug into our mu S formula, giving us tan of 7.13, giving us mu S final of 0.125. For our MK, our tan angle is 0.20 divided by 1.2, which gives us an angle of 9.46 degrees. On our acceleration came out to 0.11. Plugging those two numbers in, we get our mu K equals negative 0.11 plus 9.81 sine of 9.46 divided by 9.81 cosine of 9.46, which gives us an MK of 0.155. Gathering our mu S's, we have 0.121 plus 0.123 plus 0.125 divided by 3, which gives us an average mu S of 0.123. For our mu K, we have 0.128 plus 0.139 plus 0.155 divided by 3, which gives us an average mu K of 0.141.
The importance of us repeating this experiment multiple times was to get accurate data in order to turn it into an average number. Not only did we have to repeat the process multiple times on a flat surface, but on an inclined plane as well. With these numbers, we were able to use some equations provided to us by our TA in order to find our coefficient of kinetic and static friction.